In this lecture video, we're going to be looking at numerical summaries of a data set. We'll look at two broad categories of numerical measures, measures of location and measures of dispersion. Now, measures of location give us some idea of where a data set, a numerical data set, is on the number line. Measures of location that we'll look at are the arithmetic mean, the median, the mode, the geometric mean, and then percentiles and quartiles. Now let's start off by looking at the arithmetic mean, or more typically called just the mean. You know this as the average, for example. The arithmetic mean is the sum of the data values in a data set divided by the number of data values in that data set. Now the arithmetic mean has as an interpretation, a physical interpretation, the center of mass of a data set. And so if we think about taking these numeric values in the data set and plotting them on a horizontal axis, and then let's take a fulcrum and slide it underneath that axis. In some positions, that horizontal axis will be tipping to the right. If we move that fulcrum over to the right, then at some point that horizontal axis is going to be tipping to the left. So we can think of it as like a teeter-totter. The point at which that horizontal axis would balance is the center of mass of the data set. That's the location of the arithmetic mean. And so that gives us a physical interpretation of what the arithmetic mean is. Now, one of the characteristics of the arithmetic mean is that it uses all of the data in its calculation. Now, that may seem like an odd characteristic to point out, but as we'll see, some of the measures of location that we'll look at actually don't have this characteristic. But now we point this out that the arithmetic mean uses all of the data in the data set in its calculation, because in doing that, that renders the arithmetic mean somewhat sensitive to extreme values. So as an example, let's suppose that the data values ranged anywhere from 0 to 100. But in doing the data entry of the values, let's suppose that the largest value is actually 100, but we accidentally enter 1000 for that data value. Well, you can imagine that what that's going to do to the balance point, right? If we, instead of plotting that point at 100 where it should be, if we take it out and plot it at 1000, well, then that's going to shift or cause that balance point to shift out to the right. So that is what we mean by the arithmetic mean being sensitive to extreme values. All you've got to do really is have one value that is extreme, and it can really impact the location of the mean. And when I say, let me just say that when we talk about extreme values, we're not necessarily talking about data values that are in error, like I discussed, maybe a data entry error, but that's not always the case. We could have legitimate data values, and some of which are extreme. But the point is that those extreme values do impact the value of the arithmetic mean. Now, the other thing that I would point out is that for a given data set, the arithmetic mean is unique. In other words, there's only one value for that arithmetic mean. Now, again, that may seem like an unusual or odd characteristic to point out, but again, we'll see that for at least some of these measures of location, uniqueness is not a characteristic. But for the arithmetic mean, we can be sure that for a given data set, there's one and only one mean. I actually ought to say one other thing, that it's not listed here, but for a given data set, the arithmetic mean does exist. And so we know that for a given data set, the arithmetic mean exists, and it's unique. It uses all of the data values in the data set, and it is somewhat sensitive to extreme values. And then finally, in order to have a meaningful value for the arithmetic mean, or for its calculation and interpretation to be meaningful, the data in your data set have to be either at the ratio or the interval level. So at least at the interval level for the arithmetic mean to make any sense. Okay, the next measure of location that we'll look at is called the median. And the median is a real number that satisfies two conditions. The first condition is that it is greater than or equal to at least half of the observations in the data set. The second observation, or the second characteristic, is that the median is less than or equal to at least half of the values or observations in the data set. So in order for a real number to satisfy the definition of being a median, it has to satisfy both of these criteria, both of these conditions. Now, the interpretation of the median is that it divides the data set roughly in half. And a characteristic of the median is that it does not use all of the actual data values in its calculation. In determining the value of a data set, we use either the middle value of the data set, or if we've got an even number of observations, we average the two middle values. And so in that case, we're using at most two values, two of the actual data values in the data set to calculate the median. Now, because the median does not use all of the values in the data set in its calculation, and in particular really uses at most two data values, then because of that, the median is not sensitive to a few extreme values. In addition, the median is not unique. For a given data set, there may be more than one value that satisfies the conditions of being a median. Now, in order for the median to make sense, to calculate, again, the data need to be at the interval or the ratio level. Now, how do we calculate the median? Remember that we're going to use only, at most, two values from the data set. Either, if we have an odd number of observations, we're going to use the middle value. For an odd number of observations, there is one distinct middle value. If we have an even number of observations, then there's no middle value. There are two middle values. And so we're going to use either one or two values out of the data set to calculate the median. All right, and so the way we do this is to first sort the data in ascending order. So we're going to calculate or construct an ascending data array. And then if the number of observations n is odd, then there's a single middle value, and the middle value is the median. The median is the middle value of that data set. So the median is the value that is in position n plus 1 over 2 in that ascending data array. On the other hand, if we have an even number of observations, then we've got two middle values, and the median, by convention, will be the arithmetic mean of the two middle values, the values at positions n over 2 and n over 2 plus 1 in that ascending data array. Now, by using this convention where we calculate the arithmetic mean of the two middle values, that's always going to give us a unique value for the median when we have an even number of observations. If we were not using that convention, then if we had an even number of observations, and if the two middle values were not equal, then any value greater than or equal to the smaller of those two values and less than or equal to the larger of those two values would satisfy the definition of a median. And so in that case, then there would actually be an infinite number of values that would satisfy the definition of the median. But in order to avoid confusion and things like that, if we have an even number of observations, then what we're going to do is to calculate the arithmetic mean, the arithmetic average of those two middle values, and use that as the median. All right, the next measure of location is the mode, and the mode is a data value with the greatest frequency of occurrence. Now, notice that I've not said that it's a number, all right? It's a data value, and the mode will be a value from the data set. Let me just back up a second. The median is not necessarily a value in the data set. If you have an odd number of observations, then the median will be a value in the data set. But if you have an even number of observations, then if the two middle values are not equal, and we use this particular convention, then the median will not be an actual value in the data set. But that's no problem at all. That's just a characteristic that I'm pointing out. But for the mode, because or based on its definition, the mode of a data set does have to be a value in that data set. Now, a couple characteristics of using the mode as a measure of location, and I think it would be fair to call these disadvantages of using the mode, is that the mode may fail to exist. And so, for example, if you don't have any repeated values, if the values in your data set are all unique, then there's no value in your data set that occurs more than once, so there's no data value with the greatest frequency of occurrence. I guess you could say that every observation has the same frequency of occurrence, and so in that case, we would say that we would typically describe that as saying that the mode does not exist. Now, on the other hand, it may be that you've got two or more data values in the data set that occur the same number of times, and that the number of times being greater than one. And so there may be a situation where you've got three data values, each occurring 4 times. And so in that case, there's no, you've got 3 modes, all right? And, so the mode is not unique. One of the advantages to using the mode is that you can use the mode as a measure of location for data at all 4 levels: the nominal level, the ordinal level, the interval level, and the ratio level. However, as you move up the progression from lower data levels to higher data levels, it's more likely that you're going to run into one of these kinds of problems. Either the mode failing to, typically the mode failing to exist would be something that would happen as you move up to interval level data or ratio level data. So those are some characteristics of the mode as a measure of location. The next measure of location is the geometric mean, and by definition, this is the nth root of the product of the n data values. Now, in order to be able to calculate this at all data values must be positive. They can't be negative. I suppose you could have a 0 value, but if that happens, that's actually not. Well, you could. That could happen, but typically this is used in situations where the data values are all positive. Now, the place where this might show up, this is not very commonly used in most statistical applications, but there are some situations in which it's used, and those would be, for example, if you're dealing with data where you're taking the log, let's say the natural log of the data values. And by the way, in order to be able to do that, the data values have to be positive. So that's why I was saying that typically this would be restricted to those situations where the data values are all positive. So let's think of a situation, or let's consider the situation where we may be working on the log scale, right? And so let's say we're taking the natural log of the positive data values. And then once we do that, we have a transform variable, a log transform variable. And once we do that, then we might start working with the arithmetic mean of those transformed variables. And in doing that, there are situations where at some point you might want to, after calculating the arithmetic mean, the average of those log transformed variables, you want to transform that back into the original scale. And so you would do that by exponentiating that arithmetic mean of the logged values. And if you do that, then you're back to talking about the geometric mean. But like I said, this is not used very often, but we do bring it to your attention just in case you do see it. One characteristic of the geometric mean is that for a given data set where you could actually calculate it, in other words, where the data values are all positive, then there's one and only one geometric mean. The geometric mean is unique for a given data set. Again, in order to make sense to calculate a geometric mean, the data need to be at least at the interval level, so the interval level or the ratio level. Now, the next measure or measures of location, because these actually give us 99 different measures, are the percentiles. And so a level k percentile of a data set, which I'll denote by p sub k, is a value, it's a real number that satisfies 2 conditions, all right? It's a number that is both greater than or equal to at least k% of the observations, and then also less than or equal to 1 minus k% of the observations. And actually I should have a 100 minus k here, and you'll see why in a second. So make that correction in your notes. So this should be 100 minus k%. So for example, if we were talking about the 10th percentile, all right, so p sub 10, let's say, then that would be a real number that is greater than or equal to at least 10% of the data and less than or equal to 90% of the data, all right? Okay, now, and Let me also say this should look kind of familiar. This is reminiscent of how we define the median of a data set. And in fact, the median is the 50th percentile of the data set. Now, the percentiles are not unique, and that should not be a surprise given that the median was not unique, and so the percentiles are also not unique. And there are 99 percentiles, P1 through P99. Well, there are 99 whole number percentiles, let me say it that. We can always talk about fractional percentiles, but we're talking about the whole number percentiles when we say that there are 99 of them. These 99 whole number percentiles divide a data set into 100 roughly equal parts. So let's talk about now how to find the percentiles. So to find a level K percentile of a data set with n observations, we do the following. We first sort the data in ascending order, so we create an ascending data array. And then let I be an integer between the sample size n times k over 100 and n times k over 100 plus 1 inclusive. In other words, I is an integer between that lower value and this upper value. And then once we do that, the data value in position I of the ascending data array is a level K percentile of the data set. Now, in a given situation, in a given data set for a given percentile, it may be the case that there are two integers that satisfy this condition. In that case, you can take either one of the integers or use either one of the integers and take either one of the corresponding data values in that ascending data array. And then from the percentiles, we can get the quartiles. Now, there are 3 quartiles, and they are defined in terms of the percentiles. Q1 is the 25th percentile by definition. Q2, the second quartile, is by definition the 50th percentile, or the median of the data set. And then Q3, by definition, is the 75th percentile, P75. The quartiles divide a data set into 4 roughly equal parts. And as you guessed, because the percentiles are not unique, the quartiles are not unique either. Now, if I'm going to use something like a percentile, I will typically use the quartiles. I typically don't need the resolution provided by the percentiles. The quartiles typically provide an adequate representation of location in this manner. So those are the measures of location that we're discussing at this point. We're going to go into more detail on how to calculate some of these things, in particular the arithmetic mean, and in a subsequent lecture video. At this point, we just wanted to give some definitions and talk about the characteristics of these quantities and, in general, how to calculate them.